Hello guys, welcome to Mastery by. In this video, you are going to know about an experiment, which will break the physics. The experiment I'm going to explain is the Muon G2 experiment. So let's get started. Muon G-2 is a particle physics experiment at Fermilab to measure the anomalous magnetic dipole moment of a muon to a precision of 0.14 ppm, which will be a sensitive test of the standard model. It might also provide evidence of the existence of entirely new particles. The muon, like its lighter sibling the electron, acts like a spinning magnet. The parameter known as the G factor indicates how strong the magnet is and the rate of its gyration. The value of G is slightly larger than 2, hence the name of the experiment. This difference from 2, the anomalous part, is caused by higher-order contributions from quantum field theory. In measuring G-2 with high precision and comparing its value to the theoretical prediction, physicists will discover whether the experiment agrees with theory. Any deviation would point to as yet undiscovered subatomic particles that exist in nature. For data-taking periods, Run 1, Run 2, Run 3, and Run 4 have been completed, with Run 5 currently ongoing. The results from the analysis of the Run 1 data were announced and published on April 7, 2021. The physicists reported that results from recent studies involving the particle challenged the standard model and, accordingly, may require an updating of currently understood physics. The first Muon G-2 experiments began at CERN in 1959 at the initiative of Leon Lederman. A group of 6 physicists formed the first experiment, using the synchrocyclotron at CERN. The first results were published in 1961, with a 2% precision with respect to the theoretical value, and then the second ones with this time a 0.4% precision, hence validating the quantum electrodynamics theory. A second experiment started in 1966 with a new group, working this time with the proton synchrotron, still at CERN. The results were then 25 times more precise than the previous ones, and showed a quantitative discrepancy between the experimental values and the theoretical ones, and thus required the physicists to recalculate their theoretical model. The third experiment, which started in 1969, published its final results in 1979, confirming the theory with a precision of 0.0007%. The United States took over the G-2 experiment in 1984. The next stage of Muon G-2 research was conducted at the Brookhaven National Laboratory, alternating gradient synchrotron. The experiment was done similarly to the last of the CERN experiments with the goal of having 20 times better precision. The technique involved storing 3.094 GeV muons in a uniform measured magnetic field and observing the difference of the muon spin precession and rotation frequency via detection of the muon decay electrons. The advance in precision relied crucially on a much more intense beam than was available at CERN and the injection of muons into the storage ring, whereas the previous CERN experiments had injected pions into the storage ring, of which only a small fraction decay, into muons that are stored. The experiment used a much more uniform magnetic field, using a superferric superconducting storage ring magnet, a passive superconducting inflector magnet, fast muon kickers to deflect the injected muons onto stored orbits, a beam tube NMR trolley that could map the magnetic field in the storage region, and numerous other experimental advances. The experiment took data with positive and negative muons between 1997 and 2001. Fermilab is continuing the experiment, conducted at Brookhaven National Laboratory, to measure the anomalous magnetic dipole moment of the muon. The Brookhaven experiment ended in 2001, but 10 years later, Fermilab acquired the equipment and is working to make a more accurate measurement, smaller sigma, which will either eliminate the discrepancy or confirm it as an experimentally observable example of physics beyond the standard model. The magnet was refurbished and powered on in September 2015, and has been confirmed to have the same 1.3 ppm basic magnetic field uniformity that it had before the move. As of October 2016, the magnet has been rebuilt and carefully shimmed to produce a highly uniform magnetic field. New efforts at Fermilab have resulted in a threefold improved overall uniformity, which is important for the new measurement at its higher precision.
That's it for today's video. Thanks for watching. If you like this video, then hit the like button and consider subscribing to our channel if you want to see more like it, as well as share it with your friends and family.